In the last two episodes, we fit a straight line to data using gradient descent. But here's the problem. The real world isn't linear. House prices don't follow a straight line. Language doesn't follow a straight line. Images definitely don't follow a straight line. So what do? We stack linear functions together, add one simple trick, and suddenly we can learn anything. Welcome to neural networks. Let's see why a single line fails. Here's some data that follows a curve. No matter how we adjust W and B, our line can't capture this pattern. We need something more expressive. But here's a surprising fact. If you combine two linear functions, you still get a linear function. W 2 times W 1 times X plus some constant. That's still just a line. Stacking linear on linear gives you linear. So how do neural networks escape this trap? The answer is one simple trick. After each linear transformation, apply a nonlinear function. The most popular one today is called ReLU, rectified linear unit. It does something almost stupidly simple. If the input is positive, keep it. If it's negative, set it to 0. That's it, max of 0 and x. But this tiny non-linearity changes everything. Now when you stack layers, each layer can bend the function in a new place. 2 layers can model any curve with corners. 3 layers, 4 layers, you can approximate any function. Let's build a neural network from scratch. We start with an input, say the size of a house. This goes into our first layer, let's say 3 neurons. Each neuron computes a linear function, W times X plus B, then applies ReLU. So neuron 1 outputs ReLU of W1X plus B1. Neuron 2 outputs ReLU of W2X plus B2. Neuron 3 outputs ReLU of W3X plus B3. These 3 outputs feed into a final neuron, which combines them. The output is V, 1 times a 1 plus V, 2 times a 2 plus V, 3 times a 3 plus C. That's our prediction. This network has 3 times 2 plus 4 equals 10 parameters. Not too like linear regression, but not a billion either. Yet it can model curves, peaks, valleys, things a line never could. Here's the beautiful part. Everything I just described, all the weights, all the neurons, can be written as matrix multiplication. The input is a vector. The weights of each layer form a matrix. A forward pass through the network is just multiply by a matrix, add a bias vector, apply ReLU, repeat, layer after layer. That's why GPUs are so important for AI. They're designed for fast matrix multiplication. A neural network with a billion parameters is just a sequence of very large matrix multiplications with ReLU sprinkled in between. And how do we train this? The exact same way as linear regression. Forward pass, push data through the network, get a prediction. Compute the loss, same mean squared error. Backpropagation, compute the gradient of the loss with respect to every single weight using the chain rule. Update every weight with gradient descent. The chain rule propagates the error backward through the layers. That's why it's called backpropagation. Each layer asks, how much did I contribute to the error, and adjusts accordingly. Here's the theoretical guarantee that makes neural networks special. The Universal Approximation Theorem says a neural network with just one hidden layer and enough neurons can approximate any continuous function to any desired accuracy. Any function. This was proven in 1989 by George Cybenko. It means neural networks aren't just flexible. They're mathematically universal. Given enough neurons and enough data, they can learn any pattern that exists. Our tiny network had 10 parameters and one hidden layer. Modern AI models scale this up dramatically. GPT-4 has roughly 1 trillion parameters, hundreds of layers, and processes not numbers but tokens, pieces of text converted to vectors. But the math is identical, matrix multiplications. ReLU, or its cousins like GeLU, gradient descent, backpropagation. The difference is scale. And that's what makes this series powerful. Once you understand the math at small scale, you understand it at every scale. Next time we'll look at backpropagation in detail. How the chain rule lets you efficiently compute gradients through hundreds of layers, and why it's the most important algorithm in modern AI. If you learned something today, subscribe and share this with someone who wants to understand how AI actually works. See you in the next one.